Okay, let us start the today's session. So before enter into the today's class, let's see what we studied in the previous class. We started with the test bench program. How to write the test bench Verilog program. So what is the need of the test bench program here? Like normally when you're writing a one Verilog program, you need to test. So if you want to test in the sense through the another one more program, you can pass the test vectors, or we can say these are the values. That is what meaning of this values we can pass through the another program that is called as test bench program. With the use of the test bench program, easily we can test even source code. The example we'll see. Now what we'll do, we'll see the one more example with the vector values, how we can pass the vector values. Next, second thing is here, what we've seen in the sense, like we used initial begin end we used. So as the Verilog, the initial statement begin and end, whatever the statements you written within the begin end, it will execute only once. So as per this, so what will be your simulation time? Here we need to add the timing delays. Which is the timing delay? The timing delay will be represented as hash in the Verilog. Especially in the Verilog, the hash represents timing delay. The hash 5 in the sense that indicates what? It indicates that is after 5 screen time units. That is the meaning of that. So if your simulation window is nanosecond or millisecond or picosecond, then I can say that is after 5 millisecond or after 5 picosecond. Like that we can mean it. So we see how these waveforms are generated from these values. That is what we see. So now next what we do, let us write for the Verilog test bench. So now I'm not going to write the program for multiplexer because as you know already we written. So directly I'm going for test bench program here. Let me write directly module mux underscore test. This is my module name. Followed by, in this we know that what you have to do. Now very important thing in the test bench program, the Verilog test bench program doesn't have the inputs and the outputs, because in our main program we'll give inputs and the outputs, but in the test bench program there is no input and output. Instead of that, what you have to do, the inputs are declared as registers, the outputs are declared as wire. That is very, very important. So register, what are the inputs of multiplexer means? The multiplexer will have 4:1 in the sense 4 input. So what I will do, it is nothing but 3:0. It is I will say. This is I4 input. Next, one more register. What is the one more register? Selection line. It's an indicate how many selection? 4:1 in the sense 2 selection line. So I'll say 1:0 cell. Selection line, I'll tell us selection line this. Next, output is single output. So wire Y. Yes. So now we made register I, register selection wire Y. Now you assume our module name of the main program of test bench program is mux 421 module name. You assume like this only. So we are not writing anything. Mux 421. Next, followed by, I'll say this is my instance name M1. It will be taken. Now you should write the order here. What the order you written in the main program. In the main program, whether you written input comma output or output comma input, the same order you follow it here. Same I comma selection comma Y. Next, enter. Next, what I will do, initial. First, we must initial. Always that is very, very important. Initial. After the initial, now we are going to initialize the values. Initial, begin. More than one inputs are there, right? Begin. Okay. Next, now we'll do, what are the inputs? I is the input. Now what I will do, I is equal to input. Now you remember, initially I cannot use so many inputs. I no need to change. What I will do, I'll give some input as like 4 dash B 1010. See, this is my initialized value I. Why? Because see, 1, 2, 3, 4. Now this is my selection line. This is my output Y. These are all selection line. These are all output as I. Now you see, I pixelize the value. What is the value I am going to fix here? It is 1, 0, 1, 0. This is the value I fixed. Now let me do initialize. Next, what I will do, I will initialize the S value also. What is the S value here? Let me fix as S is equal to our selection. Selection is equal to 2-B 0, 0. I am going to initialize it. It is not mandatory. You have to make 0, 0 only. You can initialize anything. I done in the next line. Even you can do here also. No, it's not an issue. Next, let me write after some delay. That is after 10 screen time units, which you will change. Whether you will change the inputs I or S selection line, which will change. Any answer?
Select line, sir.
Selection line, because the input what I did here I fixed here only the selection line. What I will do, already the selection line 0, 0 is there. I will do the next combination. The selection is equal to 2-B 0, 1. See, after 10 delay line, what will happen? The selection will become as 0, 1. Next, again as 10. Now, what is this meaning now? After 20, that is the meaning of that, correct? So now again the selection line is goes to 2-B 1, 0 because totally 4 combination. Next, as 10 selection equal to 2-B 1, 1. Again, what you can do now, see simple example I'm doing here, and I is equal to 4-B 0, 1, 1, 1 as 10 is equal to, or I'll say actually 20 is equal to. Now as 10 selection line is equal to 2-B 1, 0. Now you will tell me the timings delay. Let me put a table over there. Then it will be very, very easy. Let me put timings here. Time. This is the time table. Next is selection, or I will say as input I. Next I will say as selection line. Next I will say as Y. Time. First initial time is 0. I hope. What is the next timings? It is 10. Next time is 20. Next time is 30. See, cumulatively I am adding actually, right? 0, 10 plus 10, 20, 30. Next is 50 actually. Next is 50. Because 30 plus 20. 50. Next is 50 plus 10. 60. Now, at time 0, what is the I value? I value is 1, 0, 1, 0. This is my I value. At time 0, what is the selection value? 0, 0. Now, what will be the Y now? When selection is 0, 0, select the 0. This is your 3. This is 2. This is 1. This is 0. Then what I'll get? I'll get as 0. I'll get. Next, you see, after 10, what is the I value now? Any answer?
Same, sir. 1, 0, 1, 0.
I will be same only 1, 0, 1, 0. But S only is changing. 0, 1. My output will be what now?
1, sir.
1. Yes. Next, after 20, what is my input here? 1, 0, 1, 0 only. Same. I is remain same only. What is the selection line now? It is 1, 0. Then what is the output now?
0.
It is 0. Okay. Next, in this, my input is 1, 0, 1, 0 only. Yes. 40. So, okay, I missed out something. Let me say. I want to say something. Yes, it will keep like this only. Yes, now 1, 0, 1, 0. What is the selection line?
1.
It is 1 1. Then output will be 1. Okay.
1.
Now you tell me here what is the value, I value.
Sir, 1010.
1010 remain same only. Next
11, sir.
selection line is 1 1 only. Then output is 1.
1.
Yes. Next here after 50. What is I now?
0 1 1
0
1.
1 1 1.
Yes, 0 1 1 because here we changed. After 50 my input is changing. Now selection line is 1 0, right? Not 1 0. What is selection line now? What is selection line? After 50,
Sir, 1 1 only.
it is 1 1 only. See, this is what you need to understand, right? Because this selection line is changing after 60 only it's changing actually. Until 50 here the previous value only will be. So it is 1 1 only. So if it is 1 1 in the sense, the output will be 0, right? Next here my input is again 0 1 1 1. My selection will be 1 0 because of this. Next we'll get as what? 1 0 means it is supposed to be 1. See, this is what we will get output like this only you will get end module. Is it clear? Any doubt in this? Do you have any queries in this? How to give? Is it clear?
No, sir.
Okay, yes, fine. So similarly, I hope you might have tried to write the test bench program. Now easily you can write the program for 4-bit triple carry adder. Yes, easily you can write no 4-bit triple carry adder. How to write 4-bit triple carry adder? The inputs will be A, B. Just only one input you can give, or you can give multiple inputs also. You can give anything. So now this is what we said, the basics of digital system design using HDL here. See here, one thing, this is what I said, circuit under design. The meaning is what? It is a design under test, or anything you can say your program. That is your main program. You can consider this one. This one I can consider as design under test. Sometimes they may call us DUT. DUT in the sense design under text. Design under test. Sometimes they may call like this. DUT. Design under test. See here, this one is in your test bench program. You can see what your test bench program will do. It will generate the input to design under test. The same the way it will given into the circuit design under test, your main program. The input will be passed, then it will process it. Then the output will be given once again to your test bench here. That is checking outputs of CUD. So these two together only I can call as test bench. The generating the inputs portion, which portion? The delay portion is there, no? That only we can call as stimulus block. See now, this is already we see, no need to say anything. You see, simple. This one already we studied. Yes, see here, I say we should not write like this. Compared to your C program here, I can say the memory module, just I return a module here. After that, the initial statement I can write. If you use the message $display, as per your C program, the $display is equivalent to printf command actually. So what you can do, you can apply this under later we study. This is we can call as system task functions in Verilog. Later we will study. This $display is equivalent to printf C in the C program. Whatever you write $display in between the bracket, you write within the double quote, that will be displayed in the console window. You can have the one console window in your system actually. In that window or message window, this message will be printed. Later we'll study these things and all. Now next we'll see the hierarchical modeling concepts, or I can say this is our hierarchical modeling concept. So here the very important, the first thing is design methodologies. Here two different types of methodologies are there. The one is top down methodology, top bottom or down, I can say top down or bottom also they may call. Top down methodology. The second one is bottom up methodology. One more thing I want to say here in this very important question. Very important question. This question they may ask the examination. This question is very important. Now almost 90%, 93% this question they will ask. Be clear? Top down methodology. Top down methodology in the sense you can see how it will be in the sense the top level is nothing but the main top module in your program. See here, you see this is the top down design methodology diagram. First is we are having the top block level. This is your top level block, or we can say top block level. I want to take a simple example with the example only there. Example, you consider we are going to take as example as the example for this top. We are going to take as nothing but 4-bit ripple carry adder or parallel adder. Okay, 4-bit ripple carry adder or parallel adder. Now we'll say RCA. I will call us RCA. How the diagram will be, that already we know, right? How the diagram will be. The sense very simple. Diagram will be like this. See, 4-bit ripple carry, it consists of 4 full adders, correct? 4 full adders. These are all full adders. This is your 4-bit ripple carry. That's complete one is nothing but 4-bit ripple carry adder. Now you can see inside this is a full adder, correct? Now in this again, what I will show here, again I'm having half adder. See, this is a half adder. From the top view, you can see which is the topmost we'll have. This is the topmost first, correct? Your top level block, that is nothing but 4-bit triple carry adder. The second, the green color which shows a full adder, 1-bit full adder, that is become a second. Then third one is nothing but your half adder. The same only here, the top level block is nothing but RCA. Because if you want to design any circuitry, we need to break the circuit. Then only it will be very easy. So what will happen when you are going for 4-bit triple carry adder, the 4-bit triple carry it consists of 4 1-bit adder. Now you come the example 8-bit triple carry adder. So how we can draw the 8-bit triple carry adder? Any answer?
2 4-bit repeat.
Yes, so you can 8-bit adder consists of, normally you may think like this, 8-bit triple carry adders consist of 8-bit full adder. No, you can see simple, it consists of 2 4-bit full adder. Then each 4-bit full adder consists of single 1-bit adder cell. Now same the way I can 16-bit parallel adder. Then it consists of 4 4-bit parallel adder. Then 4 4-bit adder which consists of 2 4-bit adder. This is like this. It's like a hierarchy. That is what I want to say. See, now you consider this is RCA. It's a 4-bit. You consider like this only. Now we need to break because it has consist of sub block. These sub blocks are we can call as full adder. Yes. These sub blocks are I can call as full adder. How many sub blocks is there? This is the example actually. So if the example I'm saying actually. This is here 1 full adder. This is also 1 full adder. Now what will happen if you see still full adder? Because until where you have to go in the sense, you need to go until the logic circuit you have to go. Now you see full adder. That full adder may have, if you are constructed using 2 half adder, then this will be a half adders, or the full adder will be made up of XOR gate, AND gate, OR gate. This is what called as leaf cells. The leaf cells are nothing but, here we can say the end, the last one, as per examples, I can say this is nothing but a logic gate. Until you should go take the hierarchy here. Let me take example the hierarchy for you. If it is a 16-bit or 64-bit, as in example as like this you consider 64-bit adder. If it is a 64-bit adder, how the hierarchy will come now? 64-bit adder in the sense simple. Can you tell me how it will come? 16-bit adder, 64-bit in the sense. Let me draw a simple single structure. 64. The 64 will be divided into how? You can divide in 2 ways. One is 32, 32. Otherwise, 16, 16, 16, 16. Is correct? I hope you understood. Yes. Is it clear what I'm saying?
Yes, sir.
Yeah, 64 can be like split into 32, 32 or 16, 16, 16. Okay. Now the 16-bit adder will be again classified into 4-bit adder. Again, this 4-bit adder will be have what? 4 1-bit adders. Correct? 1-bit adder. Now this 1-bit adder will have, what are the gates will be there? This 1-bit adder. Simple, same, this is what logic gate. It may have XOR, OR gate, AND gate. This is a one way. This is the one way. This is a one way. What is the alternate way I can say? As I said, alternate way, this is a one way. This is a one method we can say. The another method is you can draw the full adder using 2 half adder. Again you go half adder inside the half adder. Again what will have? One XOR gate on there. One AND gate will be there. So it is simple. I can say you can go till the last leaf cells. The leaf cells only I can call as logic gate or logic cell. I can say. I hope you understood this now. The same methodology, how it is coming. So the top level block, it is nothing but the main block. That is the top level. Normally the people used to say you run the top block, which is your top level block diagram in the sense your top level in the sense your complete experiment. Say example, if you are going to design one microcontroller in the sense your top level block is microcontroller. Then the microcontroller will have the consist of what and all will be there, like memory is separate, then registers are separate, then interface. So many interfaces will be there, controllers, DRAM, all those things will be there. Then that will be interfaced. You have to go dig into that. The USBs will be there. Then so many ports will be there. All the things you need to design individually. Then finally you have to interface. But when you are going to write the coding, we won't come from top level to bottom level normally. Correct? So what we will do in the sense, we will write the program. First, when you are drawing the diagram, what will do? First, we will draw a small diagram, then only go to the big diagrams. So this is called as top to bottom methodology. Is there any doubt in this? Do you have any doubt?
No, sir.
Yes, fine. So now what we'll do, let us go for bottom up design methodology. Now you can see the bottom up compared to your top level bottom. You see this diagram and this diagram. What happens? The diagram remains same. Only the arrow mark goes up. But the only difference this and that is, see here leaf cell in the top down methodology. But you can see in the bottom up it is leaf cell only. But what you are having? Not this. Yes. Subblock. You see the subblock? You see here macro cell we are having. Bottom up design methodology. Bottom up design methodology in the sense just this is like from schematic diagram to top level. So example, same example I will say. If you want to design here one full ladder, example, I'm going to go for example I'm going to take a full adder only, or I will take example for 4-bit, same 4-bit adder only. I will take example. You consider this is the RCA. This is the RCA. This is the RCA. Okay, this is the macro cell. So what is the macro cell here in the sense? This RCA will be consist of 1-bit adder, 1-bit adder. But how it has to be come in the sense? Simple example, I'll say, if you want to build a one full adder or half adder, it has to come from the logic cell. The logic cell in the sense, simple example I will take in the one simple NOT gate I will take. Okay, example I will show. This is the NOT gate symbol, as you know. Correct. But still, if people doesn't know inside this symbol what will be there. Same the way I can say, if this is the AND gate in the sense, example, if this is the AND gate, how you know when I give 1, 1, I am getting 1. Then what kind of circuit is there inside? Without knowing that only you studied the truth tables. I hope it's correct.
Yes, sir.
Have you proved your truth table for the logic gates till now? Have you proved? Because easily you might have seen for other circuits and all, okay, if I give this input, that output you get. But how you know for this AND gate 1, 8, 1, 1, when I give both are 1, 1, output is 1. How we know that? So still now what you studied in the sense, just like it's like kind of by God. The truth table is given. Yes, this is the truth table. Yes, is it so?
Yes, sir.
So, but my question is like this, okay? Then some kind of circuitry is there inside this AND gate or inside this NOT gate. This is nothing but a symbol actually. But we need to know what is the internal block diagram of this. So what I'll show simple diagram of inverter we can see. This is the inverter actually. So simple diagram I will show here now. How the inverter will be, because when I give 0, I will get 1. When I give 1, I will get 0. But how I'm getting 1? How I am getting 0? That we need to know very clearly. So what I will do, let me draw a diagram. This is the mass based diagram. Mass base in your analog or in the basic you might have studied. This is VDD, power supply. This is ground. This is your input, V in. This is your V out. See, this will be your PMOS. This is the PMOS. This is the NMOS. The circuit is CMOS circuit actually. See now, as the concept, what the concept says, PMOS when it will be on in the sense, it is like always PMOS when gate is 0. This is gate. Gate, this is source, this is drain. This is source, this is gate, then this is drain. Same. See now here, PMOS, when the PMOS will be on in the sense, when the gate is equal to 0, the PMOS is on. For NMOS, when the gate is equal to 1, the NMOS is on. So now you see when I apply Vin is equal to 0, when I apply Vin is equal to 0, what I'll get? When I apply Vin is equal to 0, the PMOS will be turned on, the NMOS is, it will be off. Now you can see there is a direct path from VDD. This is supply. V to V out. This is the path. So when I give Vin is equal to 0, I'll get VDD, V out as VDD. You consider that VDD is nothing but example as 5 volt. Example you consider. Now I'm getting 5 volt. Now same the way I'll give the input as 1 now. When I give input as 1, now what will happen next? When I give input is 1, then this will be a open circuit. This will be a open circuit. Then this will be open. When this is open, what will happen automatically? So there is a direct path from here to here. Ground to V out. So ground is normally 0 volt. So I'll get as 0. Now this is the reason when I give input is 0, I'm getting output is 1. When the input is 1, output is 0. Same like this only for NAND gate, NOR gate, different kind of structures are there. Later you will study in the VLSI design subject. There is a subject called as VLSI design in your 6th semester. You will study this. I hope you understood this. Is it clear now?
Yes, sir.
Yes. So now you can see this macro cell is nothing but here you can see that symbol. This symbol only will get here. So these leaf cells are nothing but what? Transistor based. The leaf cells are transistor based. Transistors. These are the transistor bases. So that is the difference actually. So the made up of combinedly, you have to make a combine of a leaf cells. The leaf cells will made up of macro cells. The macro cells are made up of leaf cells. The top level block is made up of macro cells. We can add n number of macro cells. This both questions are very, very important examination. They'll ask us top and bottom. So you have to draw this diagram with examples. You have to explain. See here, one simple example here given in the book. It is an example of 4-bit ripple carry counter. Now you can see here the 4-bit ripple carry counter. These are the 4-bit ripple carry counter is given here with the help of T counter. As you know, you are having two different types of counters. One is synchronous and the another one is asynchronous. Which counter it is, whether it's a synchronous or asynchronous?
Synchronous.
It is synchronous?
Asynchronous, sir.
It is a asynchronous because the output, the previous output, the Q is driving the next clock actually. Here one more thing, the clock is something, but which clock here? Is a positive edge or negative edge?
Negative, sir.
It's a negative edge. The bubble indicates negative edge. If there is no bubble in the clock, that indicates positive edge. Next, one more input is the reset. Commonly reset is there. So outputs are taken from here. So the ripple carry counter. Now what we'll do, see, this is a 4-bit ripple carry counter. Okay, 4-bit ripple carry counter. Now this is in the top to bottom. You assume us like this. Take the example as top to bottom design methodology. For that example, the top level block is 4-bit ripple carry counter. This diagram only. Now we doesn't know what is the next block I want to go. So Q, that is T flip flop. So let us go for T flip flop. This one. So let me say, what is this? We want to know what is the internal circuitry of this. Right? So let us say now. Yes, see now. Yes, now you see the same T, but the diagram is hierarchically we are showing here. You see, ripple carry counter. You see here, ripple carry counter. Then that has 4 T flip flops. Name is TFF0, TFF1, TFF2, TFF3. Again, we want to know what is there. This inside the T flip flop. We see